Hello everybody. Welcome back to our CFM webinar this month. So in the afternoon session, so we will start with Dr. Hiroki presentation. So Hiroki works for the Published Works Research Institute in Japan and studies on the durability of concrete structures. He's visiting at CFM for 1 year until next week, 21st March.
Yes.
Yep. Very short time for you now to say goodbye to us by a great seminar. So anyway, so over to you, Hiroki. Please say your presentation.
Yes, thank you for your kind introduction. So I'd like to share my slides. Can you see my screen?
Yes, perfect.
Okay, thank you. Thank you for your introduction. So yes, unfortunately, I have to my visiting research program will finish next week, but today I am really happy to make presentation here. And especially I'd like to thank Alan to give me the opportunity to stay CFM for 1 year. Thank you. So today my topic is durability of GFRP paths in concrete field investigation and microscopic observation. So today I have 3 contents. First, I'd like to introduce the background of my visiting research program, and then field investigation and microscopic observation of glass fiber reinforced polymer paths. Thank you. So first, the background of my visiting research. I work for Public Works Research Institute in Japan. It's located near Tokyo. And this picture of my research institute from above. And our main task include disaster recovery assistance because Japan has a lot of disasters such as flood and earthquake. So disaster recovery is one of our really important tasks. And also the contribution to the development and division of specifications, standards, guidelines, and test method is really important task, especially I belong to material group division, so this contribution is really important to me. And I especially focused on field-based study. This is related to durability design and maintenance issues of especially of my research interest is in concrete structures. So I'm really interested in field durability. So I normally conduct outdoor exposure test. This is a really conventional method, but it's really reliable. So I commonly conduct outdoor exposure tests in various places in Japan. For example, this concrete specimens outdoor exposure test. This is placed near the sea, so this is really a harsh environment. Also, we conduct exposure tests for repair materials for concrete, and we also conduct outdoor exposure tests for glass fiber reinforced polymer plate specimens and GFRP plate specimens and so forth. So I really interested in field durability. And next slide shows a example of the number of bridge construction in Japan. This is a different topic. And this so far, before 1980s, Japan constructed a lot of bridges. So now 40% of bridges are over 50 years old in Japan. And especially before 1980s, we have a lot of deterioration problems. So now we are really faced to maintenance problem of concrete structure. And this is an example of steel corrosion by chloride attack in concrete structures. For example, this is a bridge in a marine environment, and this has a steel corrosion because of this has a constructed based on the old specification, and this has a very thin concrete cover, so that's why this has a steel corrosion. But so far, bridge designed to the latest specifications show good durability, but we still need more durable materials to withstand harsh environment because Japan is really surrounded by the sea. So there are many harsh environments. So we still need more durable materials such as GFRP bars. And this is a life cycle cost example of a bridge damaged by steel corrosion. This is not a calculation. This is based on the actual bridge example constructed in 1960s. So this bridge was demolished even only 35 years in service. So this really deteriorated in very early stage. So only in 50 years old, this bridge had a start of repair and strengthening problem. So for example, to prevent chloride, we usually use surface coating on the surface of concrete. And also we have concrete patch to remove chloride from concrete cover. But for example, for concrete patch, we often have steel corrosion again, because to remove chloride from concrete is really difficult. So we often have this kind of deterioration even after repair maintenance work. So finally, this bridge was demolished even only after 30 years old. So this is a really fast deterioration. Then up to demolition, 250% of the original construction was reached. So steel corrosion is really a problem, and it needs a really expensive cost. So we have to solve this kind of problem to enhance durability of concrete structures. So that's why the main purpose of my visiting research program focuses on the use of glass fiber reinforced polymer GFRP bars as internal reinforcement and their durability. I know there are many applications of barrier walls in bridges, especially in the United States, in Canada. And also I have learned here, there are a lot of application of precast planks for boat ramp using GFRP bars. I know that now the Queensland government has the specification and standard drawing of precast planks for boat ramp using GFRP bars. So far I have studied this kind of GFRP bars durability. So to study the durability of GFRP bars, we normally investigate tensile properties, because tensile properties are used in the design of civil inferior structures. So tensile tests after alkaline conditioning are generally conducted. For example, we use bare bars normally, and we put the bars alkaline solution. And after that, for example, 60 degrees Celsius for 90 days, we conduct tensile test. So we will know the durability of GFRP bars by conducting immersion test and tensile test. But for study field durability, this is really difficult because we need a long specimen. So for example, based on the ASTM standard, only free length we need more than 380 millimeters. And also we need 2 times anchor length. Anchor length means this length. So normally we need more than 1 meter sample. So it is very difficult to take that kind of specimen from actual concrete bridges because it will damage actual concrete structures and it will stop traffic. So practically impossible to take a long specimen from actual concrete bridges. But on the other hand, we also have an interlaminar shear test by short beam test as shown in this picture. This will needs only length equal to 4 to 7 times bar diameter. So if we take a concrete core sample, diameter 100 millimeter, we can test interlaminar shear strength from a sample taken by actual concrete structures. So in my study during visiting research, I focused on interlaminar shear because this can be taken from actual concrete structure. So the next topic is field investigation of the durability of GFRP bars. And I have collected the field investigation of 11 to 20 years old binary ester-based GFRP bars. This is a common type of GFRP bars for civil infrastructure. And this is based on testing interlaminar shear strength. I say IRAS for interlaminar shear strength. And this is because we can test by using a small dimension sample, so we can understand the field durability of GFRP bars using a small dimension samples. And I also conducted long-term prediction based on the achievement of past CFM achievement and compared to the field durability test result to understand the reliability of GFRP bars in concrete based on IRAS. And this is so far field durability data is really limited, but I have collected experimental data based on the available literature. For example, bridge barrier from Canada and bridge decks from the United States and exposure specimen from Saudi Arabia. And I compared these field investigation results to predict the result. So I briefly explain prediction method. This is based on the past achievement of CFM. And this experiment had IRAS of binary ester-based GFRP bars, and diameter was 9.5 millimeters. And immersion test to tap water and saline solution and alkaline solution were conducted in 20, 60, 80 degrees Celsius. And this experiment had bare bars and concrete embedded bars. And the water absorption of bare bars were only 0.2% even at equilibrium. So this is example of immersion test using concrete embedded bars and bare bars. So the vertical axis is IRAS retention. This means conditioned interlaminar shear strength divided by unconditioned interlaminar shear strength. So as you can see, if we use bare bars, the IRAS retention is reduced rapidly. But if we use concrete embedded bars, IRAS retention will have higher retention. So this is because the presence of concrete cover limited the availability of moisture around the bars. So the concrete cover is has really important role for the durability of GFRP bars. And also, I briefly explain prediction method based on the RNAs model. So first, we have iris retention versus time based on logarithmic equation. Then we can have RNAs plots. So we can obtain the regression constant from this RNAs plot. Then based on this regression constant, we can convert all the data to those at the same temperature. So we can get this kind of master curve of iris retention. And also, since we have time shift factor, we can calculate master curves corresponding temperatures 4 to 26 degrees Celsius. These are corresponding to the result of field durability. This is a comparison between field durability test data and the prediction data. For example, figure A, we have this is field durability investigation data. This really agree well with prediction result. For this prediction, this has a relatively low iris retention. This is because this bar has higher water absorption. So I believe that's why this had a relatively low iris retention. For the other cases, iris retention relatively high. I believe this because of concrete was drying condition. So because if concrete is in dry condition, alkaline environment can be milder. So that's why this field durability data show relatively high iris retention. But overall, I would like to say prediction result based on alkaline solution shows a really conservative result. But on the other hand, prediction result based on tap water or saline solution shows a relatively good agreement. So in conclusion for this topic, the presence of concrete cover is really important for long-term prediction. And also the field exposure results show cross values to the predicted results of tap water or saline solution, while the predicted results of alkaline solution are really conservative. So normally we conduct immersion tests using bare bars to alkaline solution, but this can be a really conservative result. So from my study, immersion of concrete embedded bars to tap water is really had a good agreement with field environment. And this is my last presentation topic. During my visiting research, I did a lot of microscopic observations of GFRP bars because to understand the degradation of GFRP bars, it is very important to with what is the damaged components of it is fiber or resin or fiber resin interface. This is very important to understand the degradation of the GFRP bars. And I did the SEM using the JIT block, but I thought it was really difficult. Where is the position where I observed? So because not only the damaged components, damaged area is also important to understand the degradation of GFRP bars. So the location of damaged area is really important. So I tried to use the digital microscope in P11. So in my opinion, this is a really good tool to understand the degradation of GFRP bars because we have many kind of lenses which have different magnifications. For the first lenses, we have 1 to 10 millimeter scale microscopic lenses. So this really corresponds to the bar diameter 10 to 20 millimeters, which normally we use this kind of diameters. So, and then we can use another high magnification lenses. This has 100 micrometers to 1 millimeter scale. So we can observe the interface between the glass fiber and resin. And we can use even higher magnification. So this is 1 micrometer to 10 micrometer scale. So we can clearly observe the interface between the glass fiber and the resin. And the diameter of glass fiber filament is between 10 to 20 micrometers. So this is really good corresponding to observe the interface of glass fiber and resin. And I'd like to share some example of GFRP bars. So this shows untested sample of 10 millimeter bar, and this shows after alkaline conditioning and interlaminar shear strength test. So we have some damage area, and also we have horizontal cracks due to interlaminar shear test. So if we observe this area, we can see the crack with high magnification. And if we have even higher magnification, we can observe the damage between the glass fiber filament and resin. Another example, if we look at this area, we can see damage boundary. This is alkaline affected area, but this is not alkaline affected area. So we can observe the difference. If we look at higher magnification, we can see the resin is damaged, and also the fiber filament is damaged. So by using the higher low magnification to higher magnification, we can see the damage position, and we can also see the damage component of glass fiber, resin, and fiber resin interface. So this is also another example. We have 3 specimens. This has different manufacturing parameters. And this picture was taken by horizontally cut by water jet. Control means this is after interlaminar shear strength test. So we have some horizontal cracks. And after that, we had alkaline conditioning 1,000 hours and 2,000 hours and 3,000 hours. So this white color area means damaged area. I observed this white color area had resin damage and fiber filament damage and the interface damage. And as the conditioning times increases, the white damaged area increase. And as you can see, this specimen type C has the highest damaged area. So by using the digital microscope, we can observe the damaged area, so we can understand the degradation. This can help understand the degradation mechanism. So in summary, microscopic observations with the DSX 1000 in P11 are useful too for understanding the degradation of GFRP bars. And finally, the digital microscope can record the exact position of the bar, and the magnification scale corresponds to the diameter of the bar, in the glass fiber filaments enough to observe damage of GFRP bars. Thank you for your kind attention.